Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures in random signal theory. And we are still in chapter 7, which is about point estimation. And today we would like to talk about a method for point estimation, which is called the method of moments. So basically, what we have studied so far in terms of estimation is the following. So we began with our introduction of this chapter, in which we said that sometimes the unknown parameter has a very fitting estimator that just makes sense or looks logical or seems intuitive. Like, for example, if the unknown parameter is the population mean, we can estimate it using the sample mean. If the unknown parameter is the population variance, then we can estimate it using the sample variance. So this was our first idea. We had some estimators using the sample. Of course, in all these estimators, our main idea is that we have a population that contains all values, and from this population we take a smaller finite sample and we choose this sample at random. Now, we used to call this sample x1, x2 until xn. These are observations that we choose from the sample at random. These are observations that we choose from the population at random, and these observations together are called the random sample. Now, as I just mentioned in our introduction, we came across some estimators that looked intuitive, like sample mean for the population mean and sample variance for the population variance. And then later, we also studied the idea of unbiased estimators, which was a nice framework to judge an estimator which is already given to you. So if the estimator is given for a specific parameter, using this machinery of unbiased estimators by simply obtaining the expected value of the estimator, and if you find if this expected value is actually equal to the unknown parameter, then we say our estimator is unbiased. However, what was the game at that time? The game was the estimator is given to you and you judge whether it's unbiased or not. So unbiased reflects we have a good estimator. If it's biased, then the estimator might not be good. Also, if you are given two alternative estimators, you have also learned how to distinguish between them. How can you compare and choose which is better for you? Of course, you have to check whether they're unbiased or not. If both are unbiased, then we go to the variance of each one of the estimators, and the one that has a smaller variance is the one that we prefer. So all these are things that we have learned. Now, what is new today? What is new today is basically if we have a population or a random variable with an unknown parameter, how can you come up with an estimator for this parameter on your own? So it will not be given to you, but is there any systematic approach that we can use to come up with an estimator? And the answer is yes. The approach is not only one approach. Actually, we have several approaches. So if you look at the book chapter, you will find a section called methods of estimation, and we have several techniques. One of them is called the method of moments. Later, there is also the method of maximum likelihood. There is also the method of maximum likelihood, and also some other methods. However, we focus on the method of moments. So today we would like to talk to you about the method of moments, which is a way to estimate an unknown parameter or a group of unknown parameters. So what is the problem we are dealing with? We have a random variable x. Of course, that random variable represents a population. However, that random variable x has some unknown parameters, and to be able to be general, let's assume that the unknown parameters are theta 1, theta 2, theta 3, and so on until theta m. So we have m unknown parameters. If we have a specific problem, maybe the unknown parameters are 1 or 2 or 3, depending on how many parameters we have. So this is the setup. We have a random variable x. However, this random variable has some unknown parameters. Let's assume more than one in general, theta 1, theta 2, until theta m. Okay, since we have unknown parameters, what are we doing in this chapter? What was in the heart of this chapter? It is the fact that from the random variable, or equivalently from the population, we choose a sample at random. So x1, x2 until xn is a sample that we choose at random from the random variable x. These are our n observations that make up a sample. Okay, of course, once we have decided to do so, we can actually go ahead and select the sample for real. So each one of these x1, x2 will be a number, and then we can apply our estimator to get the estimate of the unknown parameters as numeric values. However, for now, x1, x2 until xn is a random sample that we take from x. So before we talk about the method of moments itself, we have to make some definitions, because these are they are basically related to things that we have studied, but the definitions are a little bit new, so we have not seen those exactly the same. So what is the moment? We distinguish between population moments and sample moments. So what is the first population moment? By definition, the first population moment is simply the expected value of x. So if x is a random variable, the expectation of x is the first population moment. So as you notice, the first population moment is nothing but the population mean, the expected value of x that we also call mu. So if we have a continuous variable x, how do we calculate the expected value of x? Simply the integral x times f of x dx. If it was a discrete variable, then it's the summation of x times f of x. So what is the second population moment? Expected value of x square. So the integral x squared times f of x dx. So what is the third population moment? By definition, the expected of x to the power of 3. What is the fourth population moment? The expected value of x to the power of 4. We can generalize in general. What is the kth population moment? The population moment number k. It is the expected value of x to the power of k, and if you have a continuous variable, this would be the integral of x to the power of k times f of x dx. These are the population moments. We call them population moments because we calculate them using the variable itself, using the random variable which is identified by a probability function f of x. On the other side, for the sample that we choose at random from the population, what is the first sample moment? By definition, the first sample moment is the summation of all xi's in the sample, so adding up all observations in the sample divided by n. So as you notice, the first sample moment is nothing but the sample mean. So the first population moment was the population mean, and the first sample moment was the sample mean. However, what is the second sample moment? It's not the sample variance. No, the second sample moment is the summation of all xi squared divided by n. So it's a definition very similar to the first moment, but the xi's are squared. So it is the summation of the observations squared divided by n. What's the third sample moment? Summation of xi to the power of 3 divided by n. So it's the summation of the cubes of the observations divided by n. In general, what is the sample moment number k, or the kth sample moment? It is the summation over all individuals in the sample, all observations in the sample, from 1 until n of xi to the power of k divided by n. So we have just defined the population moments, first, second, third, and so on, and the sample moments, first, second, third, and so on. Now, what is the method of moments then? The method of moments says the following. We create some equations that we solve together, and we are solving these equations with the purpose of finding the unknown parameters, and you will see examples. So what is the method of moments? The method of moments is that we take the first population moment and make it equal to the first sample moment. So we equate the first population moment to the first sample moment, and the second population moment to the second sample moment, and so on. Each population moment is made equal to the equivalent, or the equivalent or the corresponding sample moment. However, the question is, how many equations do we need? The number of equations has to be the same as the number of parameters. So here in this basically development, we assumed that we have m unknown parameters, so we need m equations. First population moment equal first sample moment, second population moment equals to second sample moment, all the way until mth population moment equal to the mth sample moment. So we have m equations. We are solving them together, hoping to find theta 1, theta 2 until theta m, and then we have the estimators. So let's make a note here. What about the special case in which we have only one unknown parameter? So before the special case, obviously, as we have mentioned before, the number of equations needs to be the same as the number of unknown parameters. So if we have only one unknown parameter, if we have a random variable with only one parameter, theta here, it means that to estimate theta we need only one equation, and that equation would be the first one here. First population moment is equal to the first sample moment. Now how can we apply this equation? Again, what was the first population moment from the previous slide? The first population moment was the expected value of x that we calculate from the random variable. And what is the first sample moment? It is 1 over n summation xi. This is the equation that we solve, hoping to come up with the unknown parameter on the left, and then on the right we have things related to the sample, because to estimate the unknown parameter we are assuming that the sample is chosen basically at random. So after we choose the sample, we want to estimate the unknown parameter in terms of this sample. Now let me show you the actual slide. So what you have seen here are my own notes on the issue, and the actual slide says exactly the same thing. So here in the top box we have the definitions. So if x1 and x2 until xn is random sample from a probability distribution f of x, or equivalently from a random variable x, or from a population, then we define the kth population moment as the expected value of x to the power of k, and k can be anything, 1, 2, 3. So using this we have the first moment, the second moment, the third, and so on. And the corresponding kth sample moment is simply 1 over n, and n is the size of the sample, 1 over n times the summation of xi to the power of k. Again, if we substitute k equal to 1, we have the first moment, k equal to 2, we have the second sample moment, and so on. So what is the method of moments? As we have mentioned, the method of moments is that we equate the first m population moments to the first m sample moments, assuming that we have m parameters. So I think the best way is to look at an example right away so that we see how we do that. Actually, it's very easy. However, you just need to be familiar. You just need to familiarize yourself with this new concept. So in the first example, it is not from the slides, but it's a very important type of examples. We say the following: x is a random variable with probability density function f of x is equal to 1 over 2b, and that applies for x between b and 3b. So here this probability density function has no x, so I think it's very clear to you that we have a uniform distribution. We have also a continuous variable because x is in a range between b and 3b. That probability function depends on b, and also the range for x depends on b. So obviously that function f of x, it's clearly defined. However, it still has an unknown parameter, which is this constant b. So now you see something different. So instead of the unknown parameter being mu or sigma square or these things, the unknown parameter here is just a constant. So our probability function depends on a constant b, and that constant is unknown. If we know this probability function exactly, this constant should be a number, but we don't know this number, so that's why b is our unknown parameter. So what is the question? The question says find the moment estimator for b, assuming a random sample of size n. So basically we assume that from this probability function we take a random sample of size n. What do we mean by taking a random sample of size n? If x is a variable between b and 3b, then we generate values for this x, and each time the value is between b and 3b. So this would be our x1, our x2, our x3 until xn, which is the random sample of size n. Okay, so using this random sample, we would like to estimate our unknown parameter b using the method of moments. So what was the method of moments again? The method of moments, since we have only one parameter, then we need only one equation. So we will try with the first equation. It says the first population moment is equal to the first sample moment. Again, what was the first population moment? The expected value of x. And what is the first sample moment? It is 1 over n summation xi, which is nothing but x bar. So we can also call it x bar, which is the average of our sample. Now, by putting expected of x equals to x bar, we hope to come up with an estimator for the unknown parameter b. So what should we know? As you have seen here, I'm saying the first population moment is the expected value of x. So let's calculate it for our problem here. For our probability function f of x, let's calculate the expectation, the expected value of x. We have a continuous variable between b and 3b. So to come up with the expected value of x, it is the integral from b until 3b of x times f of x dx, our normal definition. However, what was f of x? 1 over 2b here. So we substitute, since 1 over 2b is a constant, we can take it outside the integral. So we have 1 over 2b, and then the integral from b until 3b, which is the range, x dx. So 1 over 2b here is a constant. What's the integral of x? It's x squared over 2. So again, over 2 is a constant, we can take it outside. So we have x squared is the integral value, and then the limits from b until 3b. So 1 over 2b times 2 is 1 over 4b here. This is just the value of the constant outside. And then we substitute with 3b. What is 3b all squared? 9b squared minus b squared. So we have 9b squared minus b squared. Obviously 9b squared minus b squared is 8b squared, divided by 4b is 2b. So what is this 2b here? That's the value, that's the expected value of the random variable, and it came actually as it came depending on b. So depending on this parameter b. So this is the expected value of x. So what is the method of moments again? We make this equal to the first sample moment, which is x bar. So 2b, which is actually the result of the expected value of x, which we have obtained from the probability function, we make it equal to x bar, and x bar is simply the first sample moment here. The first sample moment, however, we know that the first sample moment is also called x bar, so it becomes useful, it becomes handy if we just continue with this x bar. Things are short and the equation is nice and clean. So 2b is equal to x bar. This is actually the equation that we called in general first population moment is equal to the first sample moment. 2b is equal to x bar. Why 2b is equal to x bar? X bar is the first sample moment as it is, and 2b, using the integration, we found that 2b is actually the expected value of x, which is the first population moment. Now we have one equation, 2b is equal to x bar. What do we do with this equation? We solve it for b, for the parameter. We hope to have b on a side and then everything else on the other side. So this is really easy. For this simple equation, we just divide by 2. So b is equal to x bar over 2, and this is our estimator. To give us a final answer, we just say b hat, so we just put a hat on the b. B hat is equal to x bar over 2, and this is the final answer. So the final answer to the question here is not a number, it is basically a function of the sample, and we are used, since the beginning of this chapter, we are used to the fact that the estimator of the unknown parameter is a function of our sample. And what we suggest here by applying the method of moments is that we can estimate b. So the estimator for b is x bar divided by 2. So let me make a comment here. What does this mean actually? What it means is the following. Imagine that we have a random variable with this probability function, but that probability function has an unknown parameter. According to our development using the method of moments, the suggestion is the following. So our answer using the method of moments, our result using the method of moments, suggests that we can estimate or approximate that unknown parameter b by doing the following. From the random variable, we generate a random sample. We generate a sample of size n at random. So if we really pick this sample, then we can calculate the sample mean for the sample. We add all the observations and we divide by n. We have the sample mean. Now if we divide the sample mean by 2, this is the suggested estimator for our unknown parameter b, and this is the answer. Now for that kind of question, you can think of this as problem A, and we could have a follow-up question B for the same problem that says, is the estimator that you have obtained here, that estimator which you obtained as x bar over 2, is this an unbiased estimator, or is it a biased estimator? Sometimes we can find an answer to this question, especially if the estimator is simply something linear. So linear in our sample, just the summation of the sample, nothing square or nothing cubed. Okay. How do we find out if an estimator is unbiased? We do the following. We get the expected value of the estimator. So we get the expected value of our estimator for B that we called B hat. What was the estimator for B? In our previous slide, it was X bar divided by 2. So we need to get the expected value of X bar divided by 2. Now to get this, we have to replace X bar with its definition. What was the definition of X bar? It was X1 plus X2 plus until plus Xn divided by n. And since we have over 2 as well, so we need to get the expected value of X1 plus X2 plus Xn and so on until plus Xn divided by 2n. So this is what we need to get the expected value for. So as you notice, everything goes back to the linear combinations of chapter 5. That's why we cared about it. So what is the expected value of this linear combination? So again, all these constants are the same. We can take it outside as common, and then inside we have the expected of x1, expected of x2, and each one of them is simply mu. Of course, mu is the expected value of our random variable, since x1 and x2 until xn are observations that we choose at random from this random variable. Then the expected of each is simply mu. As usual, we have this all the time. So 1 over n is a constant, and then mu plus and so on until plus mu. How many mu's are we adding? We are adding n mu's because we assumed that the sample has a size of n. We are adding n mu's, so on top we have n times mu. In the denominator we divide by 2n, so the n will cancel, and then the answer is mu over 2. We are not done yet. We're not done yet because our unknown parameter was not mu here. Our unknown parameter was b. So we need to compare this expectation versus the unknown parameter b. So there is still one more step to do. What was mu for our question here? For our question, we had a random variable which is given by that form. And in the method of moments, in part A of the question, we obtained the expected value of x that we can also call mu. So this mu here is nothing but the expected value of x, and using the integration we found it's equal to 2b already. So here this mu over 2, if we substitute, it is 2b over 2. 2 will cancel, and the answer is b. So what did we just find out? We found out that the expected value of our estimator is equal to b. And guess what? B was our unknown parameter. Since the expectation of the estimator is equal to the actual unknown parameter, then our estimator is an unbiased estimator. So this estimator that was suggested using the method of moments, which is simply, once you choose the sample, calculate the sample mean x bar and divide it by 2. And this is supposed to be an estimator for B. This is supposed to be an estimator for B. Now that estimator that we came up with using the method of moments, we have also verified that it is an unbiased estimator. Now we have another example that comes from the slides. You will see the slides coming next. So we are solving this example here. So what is this example about? The example says the following. Random variable x is a normal random variable with unknown mu and sigma square. Of course, you know that the normal random variable has two parameters, mu and sigma square. In this question, it is mentioned that both of them are unknown. So we have two parameters. We know that our population has a normal distribution. We have a normally distributed population. However, mu and sigma square, both of them are unknown. So what is the question? Find moment estimators for both mu and sigma square. So we need to come up with two estimators, one for mu and one for sigma square, using the method of moments, assuming a random sample of size n. So always assuming that from this distribution we take a random sample of size n. Now, what was the method of moments again? What is the method of moments about? The first population moment is put equal to the first sample moment, and the second population moment is put equal to the second sample moment. So what was the first population moment? It's the expected value of x. And what's the first sample moment? X bar. So the first equation is expected value of x is equal to x bar. What about the second equation? The second population moment, which is the expectation of x square, we put it equal to the second sample moment, which is 1 over n summation of the xi. Now that on the right, it stays as it is. Basically, our job is to find estimators for mu and sigma square in terms of the sample. So assuming that we have the sample, we need to provide estimators for mu and sigma square in terms of this sample. So using the first equation, what was the first equation again? Expected of x is equal to x bar. Now we have a normal distribution. And as usual in the normal distribution, we cannot integrate. So the approach will not be exactly the same as here. Here we provided the population moment, the expected value of x using the integration of our probability function. But here we have to do something else. However, we are lucky. The expected value of x for a normal distribution, isn't it the same as mu, which is the unknown parameter? So on the left here, we can call it mu, and on the right we have x bar, so it means that we are done. Since on the left we have the unknown parameter and on the right we have a function of the sample, it means we have our estimator, and we can just put a little hat on top of the mu. We say mu hat is equal to x bar, which means we have the estimator for mu already. So we just need to use the second equation to come up with an estimator for sigma square. Now, sigma square, what do we know about sigma square? Sigma square is basically the variance of x. What was the definition of the variance? Because here we don't have the variance itself. In the estimator equation, we have the expected of x square. It is not the same as the variance, so we cannot simply say this is sigma square. No, this is the expected of x square. Luckily, the expected of x square is closely related to the variance. Actually, we know that for any random variable in the world, sigma square, or the variance, is defined as the expected of x square minus mu square. Isn't it correct? This is very well known to you. Sigma square, which is the variance, is equal to the expected of x square minus mu square. If I need the expected of x square alone, here we can take it on one side and then we add mu square to the other side, so the expected of x square is sigma square plus mu square. We haven't used this equation before because we never needed it, but this equation is true for any random variable, and it simply comes from the definition of the variance. The expected of x square, which is the second population moment, is always sigma square plus mu square. So we can use this in the second equation. So on the left, we have sigma square plus mu square, and on the right, we have this form, which is the second moment, which depends on the sample that we have chosen at random. So let's continue. From equation 2, I'm restating equation 2 again. Expected of x square is equal to 1 over n summation xi square. This is the sample. This is the moment equation. The second equation for the method of the moments. Second population mean is equal to the second sample mean. And now we replace this by sigma square plus mu square, as we have worked out here. Sigma square plus mu square is equal to 1 over n summation xi square. What should we solve for? We should solve for sigma square because we still need an estimator for sigma square. So we can subtract this from the other side. So sigma square is equal to 1 over n summation xi square minus mu square. And since we need the estimator for sigma square, everything on the right needs to be in terms of the sample. So what we can do here is that we can replace mu with its estimator that we have obtained from equation 1. Mu is estimated using x bar, so that's why we remove mu and we put x bar. Of course it will be squared because we have mu squared here. So sigma square, this equation becomes sigma square is equal to 1 over n summation xi squared minus x bar all squared. And since everything depends on the sample, it means that we have the estimator. So let's put a little hat. So the estimator for sigma square can be calculated as 1 over n summation xi squared minus x bar all squared. So let me just combine these two answers. So this is the estimator of the first parameter, and this is the estimator of the second parameter, which solves the problem. Now, to understand what we're doing here, let me summarize something. So we have a normal distribution. Imagine we say that the students' GPAs has a normal distribution, but we don't know mu and we don't know sigma square. How can we possibly estimate mu and sigma square? According to our development using the method of moments, what our solution suggests is the following. From this population, which is, let's say, the population of students' GPAs, choose a sample at random from the population. Let's say I choose our class. I'm trying to interpret the meaning of this answer. So just to avoid that you're mechanically answering the question and providing the answer without understanding what's behind this answer. So I'm trying to provide an interpretation for what we have done so that you understand the meaning itself. Okay, so we assume that we have a population of student GPAs. We know it has a normal distribution. However, we don't know mu and we don't know sigma square. What our answer that was developed using the method of moments suggests is the following. From this population, go and take a sample. Let's say we have chosen our class to be the random sample. You know, our class means x1 until xn. So what is x1 in this case? The GPA of the first student in the class. x2 is the GPA of the second student. xn is the GPA of the last student. Imagine the students are listed according to their IDs. So x1 is the GPA of the first one in the list. x2 is the GPA of the second one in the list. And then xn is the GPA of the last student in the list. Now, using these GPAs, can't I just calculate x bar? Yes, we can. We add all the GPAs up and then we divide by n. This is x bar. And our solution says, please estimate mu, which is the population mean, using the sample mean x bar. So assume that mu is the same as x bar. Approximate mu as x bar. Also, our second part of the solution says the following. Now, for our sample, which has x1 until xn, we can calculate the right expression. So here in the first part, we divide 1 over n. 1 over n, n is the size of the sample. So if our class has 45 students, then this would be 1 over 45. And then we are adding the squares of the observations in the sample. We are adding the squares of the students' GPAs, and then we subtract the average of the sample all squared. This will give us a value, and we will use this as an estimator for the population variance sigma square. So this is precisely the answer to the problem that is given in the slide. However, maybe the answer has a slightly different form, so I did not necessarily simplify what you find here. I just left it as it is, and this is enough. So this finishes this lecture, and this basically finishes this chapter. And in our next part, we will solve some tutorial questions, inshallah. So I will send you the tutorial answers, and then we have a live session about these tutorial questions and answers, inshallah. Assalamu alaikum wa rahmatullah.